Okay, welcome to another Ginger Mathematician video where I'm going to finish off this paper. So we have question 6 and question 7 to do, and they're both toughies in their own way. So a big statistics question and then a big kinematics question with some calculus in there as well. So let's get started. Before I do get started though, please do think about liking and subscribing if you want more IB content, higher level, standard level or otherwise. Excuse me, let's get started. So the masses in kilograms of melons produced by a farm can be modelled by a normal distribution. I tend to label which distribution we're using, particularly at high level we have a fair few to choose from, with a mean of 2.6 kilos and standard deviation of 0.5 kilos. We want to find the probability that a melon selected at random will have a mass greater than 3 kilos. So I'm highlighting or underlining the key parts of the question. So for this one here, so this is question 6a, I'm just going to write down what information I have. So my mean is equal to 2.6. My standard deviation is equal to 0.5. And what we're looking for here is melon selected at random is greater than 3 kilos. So for our normal distribution, we want it greater than 3. So I'll just write this information down just to remind me what I'm doing. Now we are going to work with a normal distribution, which has a mean of 2.6, a standard deviation of 0.5. So just to remind myself, I'm not using binomial or something else. Because we've got a range here, we're going to be looking at norm CDF. So if we're looking for a range between something, we look at CDF. If we're looking for a specific value, then we'd use norm PDF. So what we're going to think about is the upper and lower bounds. Well, 3 is going to be our lower bound. That's where we're going to start from. Then our upper bound is going to be off to infinity. I tend to write just some huge number in. Let's put 90,000, why not? And then we've got our mean and our standard deviation, so 2.6 and 0.5. Good to show the examiner exactly what you're clicking here. So let's go to our GDC and work this out. And as you see, I've already done this earlier, so we've got 3, put some huge number in. We're going 3 to infinity, 2.6 and 0.5, giving us our final answer. I'm going to round to 3 significant figures, and then we're going to get our answer of 0.21223 SF. Kind of standard level style question, really. Just making sure you can use your GDC. Right, now we need to find the probability that 2 melons picked at random and independently, that's important, no probabilities are changing, of each other will both have a mass greater than 3 kilos. So let's get the easier question out of the way. So got B, part 1, it's got the probability of greater than 3 and greater than 3 again, but the probabilities don't change. Well, we already worked this out. We've already worked this out in the previous question. You see here I've got 0.212. So all I need to do is set the probability of that, and then because we're doing and, it's going to be multiply, ... and we're going to multiply it by itself, so the same thing again. Probability of greater than 3 and greater than 3 again. So we're going to go over to our GDC, and again we can use the handy answer function here, so you go control answer multiplied by control answer to avoid any rounding errors. And then we get our answer, which we want to do to 3 significant figures, so 0.0449. So we pop that in. 0.0449 to 3 significant figures. Okay, and for part 2, we need to be a little bit more careful. So we want to work out the total mass greater than 6 kilos. So first of all, we need to think about the expected value and the variance, okay? And the expected value works in the kind of normal way, or what you expect. So if the mean is 2.6 and we want the 2 melons together, then we simply just take the 2.6 and multiply it by 2 to give us 5.2 as our new mean. Because on average, there'll be weight of 2.6 kilos, so together there'll be an average weight of 5.2. However, the variance we have to be a bit more careful with. So what we do is we take the standard deviation, 0.5, and we square it, because remember, the variance is the square of the standard deviation, and we add it to the other standard deviation because they're the same. And if we add these two numbers together, we're going to get 0.5. However, this is the variance. This is not the standard deviation. So our standard deviation is going to be the square root of 0.5. So this is something to be very careful about between the expected value and the variance. They work in a slightly different way. Once we've got this, then we can just work it out in the normal way. So our normal distribution now is going to be 5.2, but notice our standard deviation is the square root of 0.5, so we need to be a little bit more careful. We're still going to use norm CDF in the same way that we did before. In the question, we want greater than 6, so 6 is going to be our lower bound. That huge number, 90,000 or whatever you want to use, is fine. And we pop in 5.2, and this is really important, the square root of 0.5. So we're going to put all this into our GDC. So we've got norm CDF. Notice you can just write this and it comes up, which is kind of cool. And then we've got the upper and lower bounds. So you've got 6, 90,000. You can do this through the menu as well, of course. 5.2. This is the most important part here, the square root of 0.5. And then we generate our answer of 0.12895, which is going to be 0.12923 significant figures. Okay, perfect. Right, part C. So let's have a look at part C. 1 year, due to favourable weather conditions, it's thought that the mean mass of the melons has increased. Notice increase, not change, but increase. That's important. The owner of the farm decides to take a random sample of 16 melons. Sample is important as well. Test this hypothesis at the 5% significance level. Assuming the standard deviation of the masses of the melons has not changed. That's important as well. So we do know the standard deviation. We know that from before, which is 0.5, and we need to write down H0 and H1. Okay, so let's write this in. So we've got then, well, let's let mu be, the mean mass. Notice this important, you need to use mu because we're looking for population, not for a sample. And our H0, what we're going to assume is that mu is equal to 2.6 as it was before. Okay, so everything is as normal. H1, we need to be a bit careful here. Mu is greater than 2.6. Okay, because remember in the question here, it says it wants to be greater than, or the melons have, it's thought the mean mass of the melons is increased. So therefore H1 needs to be greater than, and that's going to become important when we look at critical values a bit later on as well. Okay, so that's part C. Okay, and part D. So let's have a look. So we need to find the critical region for this test. Now this is important region, not value, which we'll talk about a bit later on. So notice that we're looking for a new population. So looking at H0, H1 for the population, and we're given the standard deviation of 0.5. So this lends ourselves to do a Z test, or look at Z testing. Now to do a Z test, we need to take some notes from the course. So notice in the context of a Z test, we use the normal distribution to model this. So to work out the sample mean, we're going to be using the mean that we got from before, and then we're going to use the variance here. Of course, we want the standard deviation for our normal distribution, so I'm going to take the necessary parts of this. So our sample mean is going to be normally distributed with the mean as is from the previous question, but we want to take the standard deviation here. This is the variance because it's squared, so we want to take the standard deviation, which is sigma over the square root of the sample size. Okay, so essentially we're going to use a normal distribution, but with this information here. And notice in the question that we are looking at a significance level of 5%, so 0.05, and we're looking for the melons increased. So the critical value, if I draw this on my diagram, it's going to be whatever this value is, such that this area is equal to 0.05, because of how my calculator operates. If we look at the area below that critical value, we want that to be 0.95. So as soon as you start talking about looking for specific values given areas, we need to be thinking inverse norm. And generally inverse norm works with the z-test. So we're looking for an area of 0.95 because the way my calculator works, it works in this direction. So looking for this area, we're given the mean, which is 2.6 from my H0, H1. And then I've got my standard deviation, which was I think 0.5, divided by the square root of the sample size, which I think is 16. There we are. And at this point, we're going to pop all this into a calculator. So we're going to work out the key value here. So we're going to work out A, let's call this A. Let's use my GDC now to work. So you go menu, statistics, distributions, inverse norm, area 0.95 because it works backwards. Our mean is 2.6. And our new standard deviation is derived by doing 0.5, our old standard deviation, divided by the square root of sample size, which is 16. Press the enter button, and it kicks out our answer of 2.80561, which we are going to round. To 3SF. Now a key error here is that you've got the critical value, but not the critical region. Okay, so the critical region is this way. This is the direction we're looking in. So our x bar is going to be greater than 2.81. It's very important. This is the critical region. Whereas what I did before, this is the critical value. So do read the question very carefully for statistics problems. Okay, right, part E. So, unknown to the farmer, the favourable weather conditions have led to all the melons, that's good, having 10% greater mass than the model described above. Find the new mean and the new standard deviation of the mass of the melons for this year. Now, they're being a bit tricky with this question because it's 10% greater mass. They haven't said it's increased by 10 kilos, for example, big melon. If it said increased by 10 kilos, then the mean would increase, but the standard deviation wouldn't. However, if it's increased by a 10% greater mass, then all we need to do, this is actually more straightforward than it looks, is so new mean is just 1.1, so increased by 10%, times the original mean, which was 2.6. So our new mean is just going to be this times this, which is 2.86, and then the new standard deviation, and this is the little bit tricky part here, we just take 1.1 and times that by 0.5. So just be careful with the reading of the question. This is the key thing. It might not seem difficult on the surface, but don't read the question correctly, you won't then get the marks. So simply new mean is 2.86 and new standard deviation is 0.55, and we've got it. Okay, and part F. So let's look at this carefully. We've got a type 2 error here. So the probability of a type 2 error. So remember the definition of a type 2 error. So we're looking for the probability of the mean actually being lower than our critical value, given that H0 is true. So mu is equal to 2.86 and standard deviation is equal to 0.55, which is what we just worked out, divided by the square root of 16, or 4, however you want to write it. So at this point, this is simply a norm CDF question. So this is just a norm CDF. The critical value, by the way, comes from part D. This was here. Now I'm going to use the unrounded version just for simplicity. You'll see it's not exactly the same answer, but it is condoned. So we've got less than 2.81, so our lower bound is, yeah, very, very low. Upper bound is 2.81. This is just some really, really, really small number. 0, 2.86, and 0.55. You can see the same formula that we used before. So we're just going to pop this into our GDC. So lower bound, yep, some very, very small number. You can just leave that, that's fine. Minus 2.81, mean is 2.86, standard deviation is 0.55. This new one, we're talking about the new situation, divided by the square root of 16. Press OK, and then we get our answer of 0.358. So that's our type 2 error. So 5823SF, like so. Just got a quick look through the mark scheme. So first thing, A and B were fairly straightforward. Yeah, part 2, just being careful with the variance. This is the key part here. Just be aware of writing your H0 and H1 correctly. So make sure you use mu and not x bar, because that's sample and not population. Yeah, click in critical region, not critical value. And yeah, notice I got 0.358. I said to accept this. Strictly speaking, I should have used the unrounded value. So that was 2.8056. If you use that value, you'll get to this answer here instead. All good. Okay, and on to question 7, the very last question. So a ball is attached to the end of a string and spun horizontally, and its position relative to a given point at time t seconds is given by this vector 1.5 cos 0.1 t squared, and then the same with sine, where all displacements are in meters. So the vector we're given here is a displacement. Show that the ball is moving in a circle with its center at 0 and state the radius of the circle. So what we need to do here is find the magnitude of this displacement. Okay, that essentially show you the distance it has traveled. So if we take A, we're going to work out the magnitude. Modulus is mathematician, but this is physics essentially. So the magnitude of the vector, which remember we're just going to use Pythagoras on. So it's going to be the square root of 1.5 cos 0.1 t squared, all squared, so lots of brackets, plus 1.5 sine, open bracket 0.1 t squared, all squared, like so. So what we'll get here, to expand this out, we're going to get 1.5 squared cos squared 0.1 t squared plus 1.5 squared sine squared 0.1 t squared. At this point I'm going to collect up the 1.5 squared under my square root. So I get 1.5 squared, open brackets. So I'm going to factorize into a single bracket. And at this stage, I need to state directly what I'm going to do at this point and use an identity from the formula sheet. So I know that cos squared x plus sine squared x, regardless of what x is always equal to 1. Therefore, I know that this is just simply going to cancel. So it's going to become 1. And so I then get the square root of 1.5 squared, which is just equal to 1.5, because these cancel, the square root and the squared. And so I get 1.5, because I'm using this identity here. Okay, so this links into here. So the radius, remember everything is in meters, as it says in the question. It's just going to be 1.5 meters, like so. Okay, so the displacement is constant. I think this is worth writing down. Notice there's no variable in our answer. Okay, all good. Let's move on. So question B. So now we need to find an expression for the velocity of the ball at time t. So this is kinematics, this section. So remember the link between velocity and displacement. We need to find the derivative. Remember the derivative of the displacement is the velocity, and the derivative of the velocity is the acceleration. So remember that diagram between displacement, velocity, acceleration, that they are derivatives of each other. So what we need to do here is actually work out the derivatives. So we're going to work out the velocity vector, and that's equal to d by dt of our original function, or vector in this case, so 1.5 cos 0.1 t squared, 1.5 sine 0.1 t squared. So we're going to be using the chain rule here to work this out. So let's be careful about this. So first we've got the 2 here, so we're going to bring that to the back. We've got the 1.5 from before as well. But then don't forget we've also got the 0.1. And remember, when we differentiate cos, we get negative sine. So we're going to get negative sine of the initial vector, sine 0.1 t squared. We do a similar process here, so we bring the 2 to the back. We have the 1.5, don't forget the 0.1 with the chain rule. And remember, when we differentiate sine, we get positive cos, so we get cos 0.1 t squared. And now if we simplify this, well, 2 times 1.5 is 3, 3 times 0.1 is 0.3. Oh, and don't forget the t, so I should have put a t in here as well. When we differentiate t squared, we get 2t. Got to put a t in there as well. So if we collect all this together, we get minus 0.3 t sine 0.1 t squared. This is the use of a chain rule, and also using the chain rule essentially. So remember, you differentiate t squared to give you 2t, then you get the 1.5 from before, then you've got the 0.1, the coefficient in front of the t squared, and this changed to a negative. Likewise here, 2t times 1.5 is 3t, times 0.1 is 0.3t. It's going to stay positive, and then we get cos 0.1 t squared. It's going to be our velocity vector, like so. That's our part 1. And then part 2. And show the velocity of the ball is always perpendicular to the position vector of the ball. So the position vector is our initial vector here, r. The velocity we've just worked out in the first part, and we need to show they're perpendicular. As soon as you see perpendicular, you need to be thinking about a dot product of 2 vectors equaling 0. So what we're going to do here then is we're going to work out what v dot r is. So we are going to work out what v was. V we've just worked out, haven't we? So we've got 0 minus 0.3 t sine 0.1 t squared, 0.3 t cos 0.1 t squared. I'm going to find the dot product with our initial vector, which was 1.5 cos 0.1 t squared, 1.5 sine 0.1 t squared. Remember, to work out dot product, all we do is multiply this by this and then add on the multiple of this times this. So this is going to be a little bit on the ugly side, but let's keep going. So minus 0.3 t sine 0.1 t squared times 1.5 cos 0.1 t squared. Okay, plus, I'm going to put this underneath, 0.3 t cos 0.1 t squared times 1.5 sine 0.1 t squared. And if we work out these, let's put these together. So we get minus 4.5 t sine 0.1 t squared cos 0.1 t squared plus 4.5 t. Okay, we're getting cos and sine the other way around, but that's fine. Hopefully, I'm going to run out of room. Oh, so close. Ah, doing so well. There we are. Stop pen. There we are. And hopefully you can see that these two things are the same. The only thing is sine and cos the other way around, but that makes no difference. And this is equal to 0. So therefore, we know that velocity and displacement or position vector are perpendicular. So yeah, real some heavy duty calculus here in order to work these things out. You can see that these two, when added together, give you 0. Therefore, V and R are perpendicular to each other. Okay, all good. Right, part C. So find an expression for the acceleration of the ball at time t. Okay, so very similar to how we did the previous question. The acceleration is equal to the derivative of the velocity vector, which is the one that we just worked out here. So minus 0.3t. Okay, this is going to take some working. Sine 0.1 t squared, and then 0.3 t cos 0.1 t squared. Right, we're going to need some room for this one. So here we're going to use what's called a product rule. So notice you've got two functions in terms of s here, in terms of t here. So the product rule goes uv dash plus vu dash. I tend to use this form of it. So the way I tend to think about this is like leave one of them the same, differentiate one of them, and then leave the other one the same, and then differentiate the other. So be careful how we do this. So let's go through this nice and carefully. So we're going to do the top part first. So I'm going to do my uv dash first. So I'm going to leave, let me color code this. Let's call this blue, and let's call this part, say, yellow. I'm going to leave that the same, because it's going to be my u. I'm going to differentiate this, and then I'm going to do it the other way around. So I'm going to differentiate this and then leave this alone. So let's put this all together. Let's go back to red. So uv dash, so we're going to leave minus 0.3t as it is. We're going to differentiate this, which we did before. So when we differentiate this, we get 2t times 0.1, and then it's going to go to cos. Okay, so that's my uv done. Plus, and we're going to go the other way around. This is much easier. If you differentiate this, we're going to get that's going to be a minus 0.3 sine 0.1 t squared, like so. Just checking everything is as it should be. Yep, good. I'm going to do the same to the bottom. So again, I do this kind of color coding idea. So I leave this the same, differentiate this, and then work the other way around. So if I do this, let's go for it. So this is going to stay the same. Differentiate this. So I get a 2t, I get a 0.1, but this is going to change to a minus because you've got cos to negative sign. And the other way around is always a bit easier, so we get 0.3 cos 0.1 t squared. And now we're going to simplify this. So let's think. So it's minus 0.3 times 2, 0.6 times 0.1 is minus 0.06 t squared cos think I've got this the other way around to the mark scheme, but that's fine. We're good. And then we've got another minus 0.3 sine 0.1 t squared. And then this one, I think we just had the positive version of this, so that's fine, 0.06 t squared. We've still got a minus here, so we've got a minus sine 0.1 t squared, and then we've got a plus here, yeah. All good. And then we've got our acceleration vector. That's some heavy-duty product rule and chain rule working there, but really well done if you got that at home. Excellent. So that's the first part. And then the second part is, so this is equal to our acceleration vector. And the string breaks when the magnitude, the magnitude of that vector we just worked out, the ball's acceleration, exceeds 20 meters per second squared. Find the value of t at the instant the string breaks. So essentially what we need to do here, with part C, is the magnitude of that vector needs to be equal to 20. Okay, so what we're going to do at that point is we're going to take the magnitude of this plus the this squared plus this squared is equal to 400. Okay, or we could write it slightly differently. So I need to color code this. I'm not going to have room to write this. So let's see if I can use some color coding to save on writing. So essentially what I'm saying is all this squared plus all what I'm going to underline now in green squared is equal to 20. So I'm going to do this by color coding rather than having to write this out again. So this squared plus this squared is equal to 20. Therefore, let's try and write this correctly. So minus the black part here, so minus 0.06 t squared cos 0.1 t squared, all squared. No, not yet. I hope I've got enough room for this. Need to write the whole thing. Okay, so the whole black thing squared plus the whole green thing is equal to 400. So all I've done at this point is I've just squared both sides to get rid of the square root. And you're probably thinking at this point, well, how do I even solve an equation like this? So we've got cos's and t's and God knows what is equal to 400. This is where we simply put this into our GDC. So all I'm going to do is I'm going to put the left-hand side into my GDC. I'm going to put a line in at 400, and I'm going to find where they intersect. Okay, so here's what I did earlier. So I've typed in that horrible blue function. Let me bring up the blue function. I've typed it all into my GDC. I've typed in 400 to give myself the straight line. And you'll see that they intersect at 18.256, which will be 18.3 seconds to the 3 significant figures. So by GDC, I'm going to need some more slides here. The last part I underestimated how many slides are required. So I'm just going to read off the x value, and that's going to be my solution. So t is equal to 18.3 seconds, and that's equal to 3sf, like so. Okay, very good. Okay, and now let's look at part 3. So what was t from before? T was equal to 18.3 seconds. We're going to need that for the next part of the question. So we found the value of t when the string breaks. How many complete revolutions has the ball completed from t equals 0 to the instant at which the string breaks? Imagine it's going round and round. It breaks at 18.3 seconds. And how many revolutions has it made before it snaps, basically? So we're going to go right back to our initial displacement function. So we're going to write down what r is, which is equal to 1.5 cos t squared, 1.5 sine. And what we're going to focus on now is the period of the function. That tells us how many revolutions are made. So what we're going to do now is going to focus on this part of the equation only. So this tells us the revolutions and what's going on. So we know the string breaks at t equals 18.3 seconds. So I'm going to work out then 0.1 times 18.3 squared. Again, please use the unrounded version when you're doing this. If you do that, you're going to get the answer of 33.329 ... Okay, and remember we're going to be working in radians here. And now we need to think, okay, about the period. How do we work out how many revolutions it makes? So we need to use that formula. Remember, if you do any sinusoidal models, let's keep it just a simple sinusoidal model. Then remember the b stands for the period of the function. So the way we work out the period of any function is we're simply going to take the angle that we've got here, and we're going to divide it by how many it takes to do a full turn, which in radians is going to be 2 pi, 316 degrees. So we're going to divide one by the other, and if we do this with radians, we're going to get 5.30. So we then know it completes 5 complete revolutions within the time it takes for it to snap. So a nice little part at the end there, using your knowledge of cos and sine and how that works in terms of period as well. So I think that's a nice question to end on. Okay, quick look at the mark scheme, so you can have a look through where you get your marks for reasoning, as well as your accuracy and method mark. You can see the heavy-duty product and chain rule that we had to work our way through. And then you've got the final answer there of 5 complete revolutions. Okay, so that's the end of this paper 2 walkthrough. These were certainly the tougher questions on the course. So if you want to get those high marks as grade 6 and grade 7, make sure you know how to work through the last 2 questions I've done. All right, bye-bye for now.